admit someone here. Yeah, right. So like I was saying, and get back to where we were. Yeah. So we go right across various classes of wireless networks. So from cellular networks, then the really long distance is where is satellite communications. Yeah. Anyway, so that is the idea. But let me now talk about on a week by week basis the details. The details of this, how we intend to cover that. So today we'll start with an intro, right? With an introduction, where basically we look at the overall what we need to cover for the entire course, and then introduce wireless communications in general. Okay, that is week 1, and this material is covered in chapter 1 in the course text. You're going to see that in a minute. In fact, maybe I should just go there directly. It is this book by Williams Stallings, right? Corey Beard and William Stallings. Stallings is a prolific writer, for networking as well as computer architecture in general. Those are his, as well as operating systems. Really, those 3 areas is what he focuses on. And this is this is a course text. There's a second one also by Stallings. That is an intro to comprehensive introduction to 5G networks. So these 2 will form the bulk of what we'll be going through in the course, right? But note these are the recommended ones, right? To feed in. All right. So first week we do an introduction. Then in week 2, we get there. In week 2, we look at the technologies that make networking possible, what we're calling transmission fundamentals. So basically here we'll be looking at the EM spectrum, basically the spectrum, the naturally occurring spectrum, and some of those signals, of course, we generate are manually generated, but they belong to those naturally occurring part of the entire spectrum, really. Then we will concentrate on time and frequency domain concepts. All right. But in short, what we'll be doing here during this is really to introduce the ideas of what signals are, how we can use them to carry data, how we can do a bit of computation to determine what are the channel capacities. In other words, what are the maximum capacities that a channel can carry. All right. And to do this, we need both time domain concepts as well as frequency domain concepts. I'll explain that when we get to that point. But for now, just think of it this way, that a signal, you can think about a signal as a function in time. Okay. In other words, if you take a snapshot in time, all right, what are the properties of that signal? And some of the key properties, of course, will include what is its size, okay, what is magnitude, and generally that will be measured in volts, all right, and also what is its frequency and what is its phase. Okay, those are the 3 big numbers that we need to keep track of for signals. All right. So that is in time domain. In frequency domain, right, what you're really looking at is if you have a composite signal, and most signals are composite, which means the signal is made up of multiples of other signals. All right. So in frequency domain, the idea is you're trying to find out is what are the components, what are the frequency components that make up that signal. Okay, that make up that signal. And for each of those components, what are the properties, all right? The fundamental properties of that signal. And generally, you'll be looking at what is the magnitude there for a given frequency component, all right? What is the magnitude? What does that component contribute to the overall signal? Okay. Anyway, so that is the focus of this topic number 2. Okay, topic number 2, and of course the other concepts we'll introduce here, like what's a bandwidth? Basically, the difference between the highest frequency and the lowest frequency. What is data rate? Which means we'll compute this, all right? And there are some 2 theorems that we'll be working with here, generally Shannon and Nyquist theorems will explain. One takes care of noisy signals, noisy channels. The other one noiseless. We'll see how that comes about. And then you also define some terminologies. Okay, like what is a digital communication? What is the difference between digital transmission, analog transmission, and so on. Okay, and also talk a bit about media. Right, media. There are two types of media. Media can either be guided or unguided. Unguided is generally what we call wireless. Okay, and generally they'll be traveling through air, but of course they can travel through fluids like water. Okay, yeah, and then the guided type, okay, is where you're thinking of the actual physical media that you use, that you use to carry as vehicles for carrying signals. All right, and basically there are three of these. This is either copper, what you call twisted copper cables, or coaxial cables, or fiber. Those are the three physical media. All right, so we talk a bit about that, and then the idea of multiplexing also is important. All right, basically meaning if you have a link, you can create multiple channels within that link, and each channel can carry its own data. So those are ideas. All right, and again we can do this either in the time domain, in the frequency domain, but we also talk of multiplexing, especially for optical communications, what we call wavelength division multiplexing. But it's, strictly speaking, is really a frequency domain concept. Anyway, so that is topic 2. In topic 3, we look at different types of networks. Okay, different types of networks. In other words, communication networks. Again, moving from short distances to medium through large distances. All right. For short distances, you think of those as local area networks. For medium distances, you think of them as metropolitan area networks. All right. And for large distances, we think of them as really wide area networks. Okay. Anyway, so we'll see those three different types in terms of geographical coverage. Okay. Then you look at terminologies. Okay. Switching terms and techniques. All right. That enable us to do those three distances. And then what are the components of a public what's called a PSTN? Right. A public switch telephone network. All right, what are its key components? Then you look at packet switching ideas, right? And then the effects of the size of a packet on a transmission system. And then importantly, and this one has to do with with services. How can we guarantee the quality of service? All right, based on the specific service that we are using on media. And when I say service, we're talking of, for example, is it radio? That is the normal radio that you listen to. Is it TV? Is it data? Okay, and so on. Okay, so each of those have different requirements. All right. So we'll talk a bit about the idea of QoS, quality of service. And the way this one generally is, is achieved really is by, and this goes back to the idea of multiplexing. For multiplexed links, which means you have different types of traffic that is going through those links. You look at which traffic, well, not you, the protocol software. They look at the priority of the traffic, right? And then decide who can jump the queue. So that if, say, for example, you come to a switch, and a switch is a very critical component in these systems. Because most of modern ones use packet switching ideas. Right? When you come to a switch, so you have an incoming packet. System needs to determine the next route the packet will take. But because many packets are coming to a switch, they tend to form a queue. All right, and that's where the delays build up. So the idea of QoS is the routing algorithms will look at the classification of the service, all right, and then determine how that packet will be treated vis-a-vis the others. Okay, so some can jump to the queue to go to the head of the queue, depending on the kind of service that the way the service has been classified. Anyway, so that is the idea. Now, in week 3, we'll start looking at this the concept protocols as well as a TCP/IP suite. Okay, suite, and generally, really, we're looking at protocol concepts. Protocol is very important because communication is a very complex sequence of events. Okay, sequence of events. Think of it this way: the way you're able to solve software problem. Sorry, the way you're able to solve problems using software is by using the divide and conquer idea. Okay, generally, when you're doing, say, software engineering or just normal software development, use the idea of modules, right? In other words, you break down the problem into modules, and then you write code for each of those modules, and then eventually they will be integrated, right? Integrate to solve the entire problem. It's a similar idea in communications, right? So we break up the communication tasks into layers, right? And then each layer will do something specific. Okay, so each layer will do something specific, and that's where, for example, most protocols use that idea, and specifically TCP/IP is broken down into five layers. Okay, the physical layer, the network layer, the IP layer, transport layer, and the application layer. Anyway, so we'll focus on these different layers in week 3. Right, and then see what each of the layers does. And of course, it's important. The concept of a router is important. Think of a router basically as what enables you to connect two networks. Now, I hope everybody is hearing me. I'm not just lumbering on my own. Are we all together?
Yeah.
Yes, we are.
Okay. All right. Okay. Thank you. So let me get back. Yeah. So I was talking about the concept of a router. We use a router basically to connect two physical networks. Why two physical networks? Because that's the way networks are actually created. Right. You start with physical networks. Generally, they will be owned by different entities. Okay, not one entity. It would be probably too expensive for any one entity to own an end-to-end network, straddling from one end of the world to the other side of the world. All right. And therefore, what you find is that there will be individual physical networks. Okay. For example, in one country, you might have, probably maybe more than one service provider. Right. And traffic is hopping from one provider to the next. All right, and then goes out of the country, goes to another country. Same thing happens like that. So think of it as the network is made up of multiple physical networks, and to connect one network to the next, because each network is using its own different parameters. So, for example, one network, or even just a portion of the network, could be using wireless. Another one is using fiber. Another one is using coax cables. Another one is using, UTP cables. All right. And when packets, when signals are going through one network to the next, we need to. You think of it basically as destroying the frame when you want to move from one network to the next, and then creating another frame that can be understood by the next network the packet is going to. So that concept of destroying and then creating another, all right, another packet. So maybe the one you are destroying was coming as light. Okay, it was a fiber portion, and the one that it needs to travel through is probably maybe a portion of a satellite. So it's wireless, okay, in the microwave range, all right. So we are destroying the packet that was in a fiber and creating another. We call them frames, and because by that time you are actually on the lower layers. Usually it's in layer 2, all right. Then you create another frame, all right, another frame that can now be understood by satellite. I just give that as an example, right? So basically, the different media we're talking about. So the job of the router, all right, essentially, besides of course doing the key thing of determining how where the packets will travel through, right? It's one of the primary roles is to ensure that the two networks that you're connecting can talk to each other, all right? So it's like an interface between two physical networks. By doing that job of creating and destroying, okay, well, destroying if you think about going in a certain direction, destroying and then creating a new frame. Anyway, so we'll talk a bit about that. You think of it as a layer 3 device. Then in week 4, we talk about the wireless channel. Okay, what are the specifics of wireless channel? We talk about antennas. We talk about radiation patterns. We talk about ideas of taking antennas a bit further. What is antenna gain? In other words, if you have an incoming signal, sorry, if one antenna sends a signal, all right, and another one is receiving, all right, you want to relate the two, all right. The gain is basically is a relation between what was sent and what has come in, right? And you would want that number generally to be more than one, minimum of one, because less than one means you are losing, okay, the signal is losing strength. We look at spectrum considerations. We look at different modes of propagation. Okay, we look at impairments that make wireless communication difficult. Okay, and maybe just very, very quickly, many things can happen in wireless transmission. So, for example, it's not always true that you'll have a line of sight communication. Okay, so for example, a very good example is take your phone. Okay, you are indoors, and yet you're able to communicate with your friends and so on through the nearest tower. Okay, through the nearest. Let me just call it radio tower, BTS in short. For BTS in short. So that signal coming from the tower to your phone, clearly that is not a direct line of sight. Okay, so many things will happen. The signal will be reflected in buildings, right? In other, structures, trees, and so on. But most of them, of course, will be man-made. All right. So there will be what are called multipath. All right, because the signals travel through different paths. So we'll do quite a bit of thinking, right, and understanding to be able to know what really happens to avoid those issues. Okay. So there'll be diffraction. There'll be reflections as well as multipath effects. We look at free space loss. Okay, free space loss. In other words, if a signal travels through space without any obstructions, all right, there'll still be a loss. Okay, because the signals always lose strength as they move from one point to the next. For example, even without thinking too much, think about a star that you're looking at. Okay, millions of light years away. The nearest being other than the sun, the nearest being 4 light years away. Okay, you can look that star directly, even if you got out of the atmosphere, because you might think it's our atmosphere that is giving you that problem. Even if you're able to get out, you could still look at that star directly, all right, without having to worry. Whereas you can't do the same if you look at our sun. Okay, why? Because the light that has traveled through those 4 million light years away has already lost lots and lots of strength. Right, so that is the idea of of signals, but specifically free space. We look at some curves, for different frequencies. What that loss looks like. All right, and then that path loss exponent for practical systems. There's a theoretical model, and then there's a practical, which is really what is implemented. Categories of noise. The idea of EB over eta naught, N naught, sorry. I'll explain more about this, but this one has to do with, if you like, how the probability of error given the original signal to noise ratio of a signal, all right, that has been normalized. Okay, we talk about more about these ideas. They're actually very central, very central ideas, right? Anyway, multipath types of fading, as well as ideas of how we can correct a channel, right? That is channel correction mechanisms, including MIMO antennas. Okay, you know, those antennas that enable us to, for example, if you think about a modern cellular phone like 5G phones actually have these. They'll not be able to operate without MIMOs. Okay, that's a requirement of 5G. We'll talk more about that later on. All right, later on. But just think of it as multiple antennas for going out and multiple antennas for receiving. Right, and signals will be split across the different different antennas. Okay. Now, hello.
Yes, this is Ken.
Hi, Ken.
So there are guys who are not yet in the meeting. They are waiting.
Oh, they're waiting. All right. Thank you for the alert. Let me look for them. Yeah, I think it's one Moses. All right. Thank you about that. Thank you for that. Yeah. Anyway, yes. So in topic 7, look at signal encoding techniques. The idea is this, right? In kind of a summary form, when we talk about signal encoding, we have alluded to the idea of a media, right? A medium, one medium, and signals are traveling through that medium. Okay. The thing is, a signal is just basically, an electromagnetic signal that is traveling through that medium. Of course, you can also have sonar, which is a bit different. But the thing is, this signal, this electrical signal, we would want it to carry data for us. How do we place data onto that signal? That is the idea of signal encoding. How do we place data, all right, on a signal so that, number one, well, you can think of it as becoming intelligent, in quotes, okay? And when it is received on the far end, you can able to unbundle that signal, right, unpack it, and be able to retrieve the data that we put in. The data can be analog, right? It could be, for example, my voice. The way, for example, you're hearing my voice, all right, it's passing through my computer, first of all, being digitized, split into packets, and then CPIP takes over, all right, using those routing mechanisms, all right, and then when it arrives on your end, all right, if it has errors, some things are happening. We talk more about how errors are handled, right, and then converted back from digital form, because it's coming as packets, back into analog form. Okay, so that your microphone can then be able to respond, correctly. So data can be analog. It can also be digital. Okay. For example, this text that you're seeing, right? This Word document that you're seeing is coming as, as a digital data. My voice is coming as analog data, and you're able to receive both of them. All right. Now, the media, that is the carriers of these signals, can also be analog, and they can also be digital. All right, they can also be digital. So what that tells you is that we actually have four different ways of combining this. Okay, so for example, you can have digital data and digital carrier, digital data, analog carrier, analog data, digital carrier, analog data, analog carrier. Okay, 4 different permutations. And depending on the permutation, there are different techniques that work best for us to place data on that. And that is the focus. That is the focus of this topic, right? Of signal encoding. Okay. So I'm not going to details. I've just explained in high level what we really mean by this, all right? But maybe I can mention a couple of them. So for example, we talk about ASK, amplitude shift keying. What you're doing is the data is digital, okay, but the carrier is analog, and we are modifying the signal by modifying its amplitude. Remember, we said there are three properties of a signal. All right, it has an amplitude which will be measured in volts. It has a phase which you can also modify, and if you modify the phase, this is what it is: quadrature phase shift keying. And you can also modify its frequency. All right, and if you do that, that is called FSK. Which is this. All right, which is that portion there. All right, so we look at these different ways of doing this. All right, and then look at the different properties that enable us to move data around. All right, and of course there are other characteristics, all right, related to these issues that we'll be talking about. So, for example, I just mentioned in passing that you can hear my voice because it's digitized. This is a technique we use. It's called PCM, passcode modulation. All right, passcode modulation. It's a very central technique. Data modulation is a sister technique. These two usually work. You can use either of these to move data. Okay, we'll explain the differences. Anyway, so that is the focus of that topic. Now, topic 6 is really a focus on a technique that enables wireless communications really to work. Okay, for example, your phone, depending on where you are, your phone is either using 4G or 5G. All right, but of course there will be some places where it will be using 3G. That is for cellular communications. All right, for cellular communications. 4G and 5G cannot work unless you use this. This is a technology that makes 4G and 5G technologies work. Okay, it's called OFDM, orthogonal frequency division multiplexing. I think in passing, all right, or in summary, what this topic is about really, or what OFDM really is about is, we take we create multiple channels, okay, that will be traveling simultaneously together. So it's actually multiplexing, and that's why this last name, this final word here, multiplexing. So we have multiple carriers. They're called subcarriers. All right. So in each of them is occupying its own channel, right? And we combine them into a link, right? A single link. But the key thing is this: the carriers are orthogonal to each other, all right? By orthogonal, what do you mean by orthogonal is it has something to do with the idea of phase, all right? It is such that any two neighboring subcarriers do not interfere with each other. Now, how can we ensure that? Is by saying, when say, think of a left and a right neighbor, think of three channels. One is the middle, one is on the left, the other one is on the right. Okay, it's a kind of an analogy. The one in the middle, when it is maximum, right? Remember, it's a okay. I know I have not explained these concepts in detail, but what happens is a channel carries its energy, that is its maximum energy, is usually at the center of the bandwidth. All right, the bandwidth that we have allocated that sub channel. All right, and for OFDM, for 4G, we use 15. Let me second. Yeah, we use 15 kilohertz channels. All right. So this 15 kilohertz channel in the middle, when it's maximum, it means the other two on the left and right, all right, will actually be zero at the center of the middle one. All right. The one in the middle, when it is maximum, all right, the other two neighboring on the left and right will be having, we actually say that it's closing. They close the x-axis if you use the idea of Cartesian coordinates, all right? The x-axis, at the when the other one is maximum. Now that is a central concept of OFDM. Okay. Now the other central idea is, and this is why this technology was not used a lot in the past. It only became possible to use it on a large scale and on small devices by having computing power. Why? Because ideally, you'd have to have oscillators for each of those subcarriers. All right, there will be 12 of them. For 4G, we use 12 sub-carriers, each of them 15 kilohertz, to make our 80 kilohertz channel. Okay, 180 kilohertz channel, and then you then have multiples of those 180. Okay, 180 kilohertz channels, so that you can use the entire bandwidth. Generally, the lowest would be like 1.4 megahertz. The next one 3 megahertz, 5 megahertz, all the way to 20 megahertz. All right, the what will be allocated to a provider like, say, Safaricom. Okay, so each of these subcarriers would require an analog oscillator. What I mean by oscillator is a generator of that 15 kilohertz. Right, on the sending side, and also on the receiving side, a 15 kilohertz oscillator to be able to extract each of these subcarriers. So the way we deal with this, okay, and this is really where the beauty of this comes in, right? The way we deal with this is actually to use math, okay, and specifically what's called let me get the correct terminology for you. Fast Fourier transforms, FFT, all right, and inverse fast Fourier transforms. All right, we use inverse when you're moving from frequency domain to time domain, and FFT when you're moving from time domain back to frequency domain, because we need to work in those two domains. Those two domains. So by using using the FFT algorithm, okay, you start with DFT, that is discrete Fourier transform, right, and then made fasts. Why fasts? Because it's an algorithm that shows you that you can actually really simplify the way the math is done to move from time domain to frequency domain, right? For the different, and then we combine the multiple carriers, so that really what's happening, for example, on your phone is doing digital signal processing, right? Which is, okay, to say that's what's happening on my computer, because I have a fiber carrier, right? Just probably like most of you, and fiber doesn't use OFDM, right? It's a different concept. But when you talk about your phone, and you're using 4G, not 3G, that is what your phone is doing, all right? It's doing digital signal processing when it is receiving signals, and also when it's sending signals to the tower, all right? To the tower, and the tower is doing the same. The tower has computers that are doing exactly the same thing to make 4G and also 5G work. Difference, of course, between 4G and 5G is in the multiples of the 12 and 15 kilohertz I told you about. 5G has more multiples of the same. I'll explain when we get there, so that we can move more data in 5G systems. Anyway, so that is OFDM. I think I've explained without going to specifics. Okay, why it's important, and how we use it. All right, how we use it. In the past, it was only used by, for example, certain applications like the military, right, who had the computing power both on the sending and the receiving side to do this heavy number crunching. All right, to be able to deal with these ideas, right? The other things are explained, like CPs. This one is to deal with multipath. Those these are wireless signals, right? They travel through different distances, and you need to can think of them as equalizing them. I'll explain really what we mean by this when we are talking about this in detail. Anyway, so that is the idea, all right? And there are some other concepts you talk about, like the single carrier. That is when your phone is sending to the tower. It doesn't use a complete FDM, right? Otherwise, it will require too much power. I'll explain about that. Now, then topic number, hang on a second. There are two topics here. There is 8. And then topic 9 is spread spectrum, right? Not quite related. This one is more of a 3G technology, spread spectrum. The idea of a 3G basically, sorry, not 3G, spread spectrum basically is we take the data that we want to send, and then we spread it across a bigger bandwidth. And that's where the spreading idea basically comes from. Think of it this way. To send a single bit, either 1 or a 0, we need more than 1 bit, okay, on the outgoing channel. which is not intuitive. Right? The way that generally we do, right? The way we do systems is we pack many bits, right? We pack more bits, and then the portion of the signal that we send, right? And we'll see this when we look at what we call constellation diagrams, is that you can get a signal, okay, and depending on its its amplitude and the phase, all right, as well as frequency not too much. The first two, you can actually receive that signal, kind of like a time snapshot, all right? And then you interpret it as, for example, a whole 6 bits, right? 6 bits rather than a single bit. So that means what? That we are transmitting 6 bits, all right? But the transmitter is almost as if it's a single bit, right? And therefore you can see it's the opposite of this idea of spreading, right? So spreading means you take your signal, spread it across a bigger, it's using more energy, right? But why do we do this? Right? We'll explain later on. But in the original days, especially in the military, was actually to ensure that an enemy, if they were able to get hold of your signal, they cannot reconstruct the original message, because the message is spread, for example, across multiple frequencies, right? Or across multiple ones and zeros, right? What happens in CDMA, right? What happens in CDMA? So we talk about actually a direct spread spectrum. We talk about frequency hopping, and we also talk about code division, multiple access. Those three form the bulk of spread spectrum. Right? I'll explain about those when we get there. You can see them down here. All right. Then in week 7 we do our midterm exams, and then week 10 we'll focus on how we deal with errors, right? How we deal with errors and a related issue, coding, coding and error control. Okay, coding in this case basically is focusing on, it's not the same, it's not this idea. Let me just go back to where we're talking about signal and data encoding. It is not this. It is not that coding. It's coding with respect to how do we place our ones and zeros so that number one, they can resist errors along the way. And if, say, errors do occur, the receiver can be able to, number one, to tell that there was an error. And number two, as happens in multiple cases for wireless communications, it can actually determine where the error was. Okay, it can do forward error correction. All right, so that's the idea behind coding, as well as dealing with. So it is this topic here of coding and error control. Okay, it's actually quite a wide topic, but we'll see how we deal. And there are various techniques that enable us to deal with these error control issues. Okay, but just think of it this way, in a very short way. There are different techniques that we can use, such that I'll just give you one example. Right. One of these, and then when we get there, we'll deal with more with them. Now, there's a concept we call convolution. You think of it this way, and this comes from signal processing. Okay, from convoluting signals. What it means is this: you have an incoming sequence of ones and zeros, but what you send is not the ones and zeros that are incoming right now. Okay, you take what had come a bit earlier, ones and zeros that have come a bit earlier. Think of them as holding them in memory briefly. All right, and then you take those old ones, and these incoming ones, you make modifications. Usually, you use exclusive ORs. All right, you make modifications, and then what you get will be the new data that you're going to send. Okay, what are you going to send? So it's called convolution. It's almost like thinking of sending a signal, but the signal you're sending has a delayed component. It is convolved. You're convolving earlier ones, right, and the current ones. We'll see how that works. We see how we use shift registers to enable us achieve that concept. Right now, the receiver, right, will do the opposite. okay, of that convolution. But more importantly, also along the path, as we'll explain, okay, we'll explain of what happens. All right, the final received signal, all right, depending on the path that it followed, all right, and how does the path, how will it know the path, which path to follow? This is not with respect to routing, is a different idea altogether, okay, based on what's called turbo coding, right? Called the turbo, turbo coding and other concepts we'll talk about. Okay, depending on the path that signal followed, we think of the received signal as a probability. All right, that this one has a high probability of being a 1 rather than a 0. Okay, based on the path that it followed. Okay, so those are the ideas we'll be talking about. I'll just give you one example, right? There are several that we'll go through, but maybe some of them are quite straightforward, like CRC. We see how that works. Okay, you take some original data, divide by some prime number, right? Append the result into the incoming block, right? And then you transmit. The receiver will do the same. It will compare the CRC code that it generates with what has come in. If they are different, it knows an error occurred. Okay, an error occurred. Or alternately, by taking the CRC code that was sent together with the data, dividing by usually it's a prime number. By that prime number, if it gets a 0, no error occurred, right? If it doesn't, there was an error, right? And then ask for retransmission, and so on. Anyway, so that is the idea of these coding and error control. And there are different mechanisms we'll be looking at, including BCH and lead Solomon code. Some of these are a bit old, but they're still very useful. Like for example, Voyager 1 and 2, right? Voyager 1 and 2 are still using, and they're still communicating. They're literally billions of kilometers away in outer space, and they're still sending signals using these lead Solomon codes. Okay, let's now talk a bit about the next topic, wireless LANs. Okay, with specific focus on 802.11, that is Wi-Fi. Right, there are different standards in here. These 802.11. There are several other standards in there with a focus on different things. All right, different things. Anyway, so the idea here is not to get to understand short communications at a short distance and the standards that make that possible. Okay, the standards that make that possible. Please note, for example, the 802.11, some of the standards within this, because there is A, B, C, D, G, and so on, right? And so on. Each of them prioritized, not prioritized. What's the correct word? Optimized. All right, optimized for either, for example, for high capacity transmission, right, or to assist errors, okay, and so on. Okay, depending on what the focus is, we'll see which standards are designed for what. Okay, so they're different. So, for example, you look at your laptop. Okay, most laptops will support the B, the G, and the N standards. Yeah. Okay, the BG and N standards. But I think the point I wanted to make is some of these also use OFDM. Okay, the OFDM, because the way the standards are defined, you choose, well, okay, it is a standard that has chosen. The standard chooses the multiplexing techniques, all right, as well as the spreading technique that it uses. So some of them will be based on frequency hopping, others will be based on OFDM, okay, on OFDM ideas. Anyway, so we'll talk about these different issues, all right. Then in topic 13, we will now go to cellular networks. Cellular, that is the what providers like Safaricom and others, the technologies that they use that make it possible for us to be able to communicate, okay, both voice as well as data. All right, I think I've given you examples of 4G and 5G without going to specifics. Okay, to specifics. If you come a bit down, for example, the first three generations, that is 1G, 2G, and 3G. Okay, 3G is still, even in fact, 2G and 3G, all the from 2G to 5G, they are all coexisting. You can go to some part of the country where the only available signals are at 2G. All right. In other words, you cannot transmit data at high speed, but you can communicate. You can send SMS, okay, and send data at very low speed. Something in the region of 14 kilobits per second. All right, is 2G. So we look at this whole spectrum when you're looking at this, right? And of course, the structure of a cellular. Let me just call it what let me call it the architecture of cellular communications. The way you think about it at very high level is, I think we know this. The provider splits the country where they operate into segments. Okay, those segments will be called PLMNs, public land management networks, and each of them will have a number of message switching centers. And the message switching center, MSN, will be in charge of several cellular areas. Okay. Now, a cell is where you have a tower, and that tower has a certain maximum radio distance where signals can go, can be received. Okay. Beyond that, the signal to noise ratio is too low. Okay, such that the device cannot distinguish data from noise. All right, from noise. But what they then do is they overlap from one tower. Think of it as a cell. From one cell to the next cell, at the center of the cell, there is a tower. And of course, depending on the generation, there are different terminologies. Okay. So when I say, for example, BTS, that is with reference to 2G. Okay. But it has become the common term to be used. All right. Otherwise, we use what we call node Bs. All right. Evolve node Bs for 4G. Okay. And NG, ENG, NB for 5G. But it basically is the same idea of a node at the center of the tower, at the center of the cell. So the cells will then overlap, okay? And the idea is, if say you have a device coming from one cell to the next cell, all right? The device will determine at what point does it start receiving from the next cell, right? The idea of handover, okay, from one cell to the next cell, okay. But the reason I'm mentioning this basically is to say that the physical land is split into cells.
Yeah,
Okay.
excuse me, sir.
Hello.
Yeah, there are people in the waiting room waiting to be let in.
Oh, okay. Yeah, there are two. Maybe they dropped or something,
Yes.
Yeah. Let's allow them to come back in. Thank you, All right. Are there any questions so far? By the way, I've spent so much time on the outline, so that when we now start looking at each of these in detail on, you can see the connections between them. All right, between the different.
I have a question.
Yes, Kevin, go ahead.
Based on our experience last semester, I'm guessing that we'll do some lab practicals.
Oh, right, yeah. This one is not lab heavy. Okay, I'll organize. I'll organize that we do a few labs. Okay, especially at least one wired lab and one wireless lab. All right, maybe three. We will see. All right, but the focus will not be on labs a lot. Yeah, but yes,
Okay.
yeah, yeah. Okay. So
I don't know if I speak for everyone, but personally, could you increase the number of labs? Right.
That's the feeling,
Yeah, because I feel like we need more of like need to be more, I guess I would say, hands-on.
Okay.
So like maybe you could let us know which software we could download and start using to explore.
Right, yeah. Okay, I don't think I've not even mentioned it here because that's not the focus. But we'll use a Cisco tool for both wired and wireless experiments. Right, experiment. Yeah. So anyway, I've had that. So I was going to give maybe 2 or 3. We'll see whether we can increase that a bit. Yeah, we can increase those labs a bit. But I've had Kevin. Thank you. Any other comments so far? Any other comments so far? Okay. Anyway, so I think I was explaining cellular networks in general, right? So I was at the point of where the physical space is split into cells. At the center of each cell, you have a tower. What is a tower? Is an antenna. The antenna sends and receives signals. Okay, I'm saying antenna, but usually there will be several antennas on the same cell. Okay, for 5G, the different antennas will be facing different directions, because they have what are called directional beams, right? So there will be a number of those, because they are MIMO, right? Multiple in, multiple output antennas. So at the center, you have a tower. The tower has antennas, and an antenna is a transceiver. It can transmit, it can receive. It has a server. There's a computer that's doing number crunching. Why? Because like I told you, right? Is either using CDMA 3G, and 3G has although for 3G, what I'm calling the computer is not at the tower, is after combining a number of towers together, where you'll find a computer. Right? Well, I'll explain how this structure works for 3G. Okay, that's where you have your server to handle a number of cells. But for 4G, each tower has its own machine, and the machine is doing the number crunching. The OFDM number crunching. There's a lot of number crunching. That has to be done, signal processing, to be able to transmit as well as receive signal, and also to handle. All right, because I've already alluded to this in general. Although usually the errors will be handled end to end. All right, but there will be some errors that can be handled at the tower location. Right, the tower location. Anyway, so I think I've said a few things about this. We talk about number of generations of this from all the way from 1G to 5G. You talk about CDMA is 3G, GSM is a 2G, but we'll be able to handle data. There is this edge. Okay, that is, this is actually 2.5G. We'll talk more about this. 3G UMTS using wideband CDMA, that is code division multiple access. All right, multiple access, and how these systems have evolved over time. Okay, so you'll notice, I think, in this topic number 13, that is week 10, is usually up to 3G, from 1G to 3G. Then we'll handle 4G in this next topic, week 14. That is a 4G as well as LTE, long-term evolution. All right. So all this is based on maybe just to highlight, with 4G, it's actually it's like the internet working inside a cellular provider. Right? You think of it as an EPC, evolved packet core. What does it mean? It means once you get to the tower, all right, once you get to the tower, the interconnection between all the different towers of that network, you think of those as interconnected by routers. All right, they're interconnected by routers, and basically then it means all the packets that are flowing through that network is just pure internet inside the cellular provider. Okay, and you can see why this works so well. All right, why this works so well. Right. However, there are some specific things that need to happen, right, inside that system. I'll explain that for 3G, for example. There are some specific servers you find at the mobile switching center, right? That enable you to go to other providers. Okay, what's called loaming. So there was what's called a visitor location register. Is a home location register to do authentication by the equipment. All those, okay, specific servers that deal with those issues, right? So when you come to 4G, the same thing will happen, but the servers are a bit different. I'll explain the differences in in 4G. Yeah, right, in 4G. And then also, depending on whether the how the frame is structured, I explain these frame types, right? Later on, right? Depending on how the frames are structured, there's what's called type 1 and type 2. Okay, and this has to do with okay, first of all, a frame. I don't want to get to a lot of detail right now, right? To avoid confusing issues. A frame basically is at a very high level. Think of it this way. I explained very loosely that when you're talking about OFDM, we have carriers, sub-carriers. There are 12 sub-carriers, okay, to make 180 kilohertz. All right, each carrier carries 15 kilohertz, okay, and therefore the 12 of them that make up, you can think of it as a complete. I don't want to use the channel, the idea of a channel, because each of those is a channel. But when you combine them, you create a symbol, and that symbol is called an OFDM symbol. Okay, OFDM symbol. Now, there is a way that you combine multiple symbols to create a frame. All right, to create this frame, right? And there are two ways that you can do this. So depending on which one you do, you end up with these two FDD, okay, FDD types of frames. All right. I'll explain about these are relay nodes, but I think maybe very quickly think of it this way. I've talked about a tower at the center of the cell. Think of this as small towers at the edge of the cell that extend the reach of the cell. Okay, they're called relay nodes. So basically, they're really like small towers, in their own respect. All right, and they're able to do what is it? They're able to re-amplify the signal from the tower, so that receive cells. Think of them as, I don't know, phones that are further away from the center of the cell can still be able to send and receive data through these relay nodes, right? Through these relay nodes. All right. Anyway, so let me leave that 4G at that time. Okay. LTE, that is a long-time evolution. It is this idea of splitting these carriers, organizing frames. Okay, different types of frames, and therefore you are able to carry depending on how many of those OFDM symbols you combine. All right, you can find for example one customer can be given, say for example, 8 gigabits of data per second. Another one can get, say, I don't know, 20 gigabits. Not giga. Let me go back. 8 megabits per second. Another can be given 20 megabits per second, depending on the service that you buy. How do you arrive at that? It is by combining this 180 kilohertz I told you about, multiples of that. Okay, multiples of that, and that gives us the structure of LTE. Okay, the original one you can only go to a certain level, but LTE Advanced you can actually go to 100 megabits per second. All right, by utilizing the upper limit, the 20 megahertz channel. You have many more 180 kilohertz splits using that. Okay, so then I think with long range communications, I think here we'll be talking about satellites communication generally. Okay, different types of satellites, low Earth orbit, medium Earth orbit, as well as geosynchronous. This geo orbit, okay, meaning a satellite is rotating at the same speed as the Earth. Okay, in other words, it takes 24 hours to make one rotation, just like the Earth does. So it means the satellite is stationary with respect to a certain point on the Earth. Okay, they're called geosynchronous satellites, and these ones orbit about 39,000 kilometers. No, 36,000 kilometers. All right. Whereas the low Earth orbit, these ones rotate about 400, up to about 2,000. Between 400 kilometers at 2,000 kilometers. They're called low Earth orbit. So this is where, for example, you'll find, the ISS, International Space Station. This is where you find the Hubble Space Station. This is where you'll find Elon Musk's thousands of satellites, okay, because they are low Earth orbit. Then MEO, medium Earth satellites. These are, for example, your GPS. Your GPS operates in this region, MEO, medium Earth orbit, between 2,000 and 20,000 kilometers. Okay, specifically, in fact, GPS is actually 20,000 kilometers, but that's the general region. Okay, general region. LEO, the low Earth orbit, need to rotate fast so as not to fall back to Earth. Okay, so what this means is every roughly 90 minutes they have to make one rotation. Whereas MEO satellites, okay, this one can, for the lower ones, about 2 hours. Okay, every 2 hours and upwards. Okay, every 2 hours they're able to make one rotation, and depending on whether they're on the upper limit, that number goes up, right? To make one complete revolution. But the key point, of course, is the satellites are just like the BTSs we're talking about for cellular communications, only that they're in the sky. The same idea, but they're in the sky, so that you can cover a much larger portion of the Earth. Okay, so with satellites, you need that satellite. So it's like a BTS. It's like a tower that is elevated, right? And then you need line of sight communication on the ground. So there will be another satellite. Usually it will be VSATs, okay, very small aperture terminal satellite, to receive as well as send signals to the and here I'm referring, for example, to the geosynchronous satellites. Okay, but that's not always the case. It can also be MEO or LEO. Okay, but in that case, what it means is because you need a satellite to be at the minimum the horizon of a given VSAT. Okay, VSAT, in other words, should be able to see it before it disappears on the other side of the horizon. So when that happens, another one needs to take over. All right, and that's why Elon Musk needs thousands of those satellites, because they are rotating at roughly 800 kilometers above the Earth. Anyway, so we'll talk a bit about other related issues in these long-range communications for wide area communications. All right. So, for example, the 802.16, this one generally falls in the sometimes you can think about this as MANS, metropolitan area. All right, metropolitan area, because of the coverage, the distance that they cover. All right, but anyway, so we talk about all these different issues. Yeah, and I think maybe just to finalize, we say a few about 5G. All right, 5G in week 13. These are loaded. It's actually a very loaded outline, right? But we need to touch on all these. All right, we need to touch on all these different areas. But the focus, okay, number one, I'll talk a bit about the architecture of 5G so that you can see how different it is, how it differs from 4G. I've already said in passing that 5G and 4G use a similar technology, OFDM. Okay, OFDM. But the way the frames are structured for 5G, all right, as well as the upper limits of the bandwidth, right? For 5G, it goes up to 100 megahertz. All right, that's the bandwidth, and for 4G, it stops at 20 megahertz. All right, the bandwidth, and therefore, with 100 megahertz, you have a very, very how do I put it? You have several spaces. Let me use that word. You have several spaces of having multiples of the 180 kilohertz, the one I told you about, before you hit the 100 megahertz. All right, and then clearly you can then see that you can actually that you're able to improve your data transmission speeds by a very big margin. Okay, so generally 5G 1 gigabit per second. They're able to handle that very well. Okay, but the focus here, and that's why we have this use case, the focus here, besides looking at the architecture, we'll also be looking at how is 5G used mainly. And you see there are three classifications. I think I have them here somewhere, the three classifications, or maybe not. Yeah, but basically the way you think about here, the focus is on architecture. So the three use cases basically are for communications with individuals, okay, what's generally called, wide broadband, all right. Then machine-to-machine communications, okay, what's called, EMMC, all right. In other words, for example, IoT devices, they're designed to use that portion of the 5G, okay, it's called that is massive machine-to-machine communications, right? MMMC, and then the third one is where you don't need high-speed communication, but you need very high reliability. Okay, you need a very high reliability. So those are called ultra-low latency, all right, as well as a highly reliable communication. So that is for example, controlling. Let's say, for example, you're talking about driverless vehicles. All right. Not only are they talking amongst themselves along the road, I'm using that word figuratively, so that you can determine what's happening to. Okay, not to the vehicles on the road, but certainly to the roadside infrastructure. Okay, and that roadside infrastructure is connected to servers in the cloud. So the communication between, for example, self-driving cars, all right, and data sitting on servers, number one, needs to be very, very reliable. And secondly, you need to have very low latency, okay, to be able to those two devices to talk to each other, so that you can achieve real-time communications. That is the core idea. Right. So we focus on those three broad categories of use cases. That is as defined by what do you call it? ITU. ITU is the one that defines that model, all right? But the other use cases defined by two others that you see, okay? Like, for example, there is this NGMN, okay? This one is a North American association. And then there is this 3GPP. This one is an association of cellular providers across the world, okay? So actually, there are three use cases that you look at. Okay, I've just given you one, the one by ITU. Okay, but the others are actually a variation of that. We'll see how that variation goes. All right, goes. Anyway, so 5G very important because and maybe just, I think in passing, let me also mention this. The way devices will be using 5G, the way they are using 5G, and they will continue using 5G, is not the normal way that we use other networks. Is by having what are called software-defined networks. In other words, it is actually programming the network so that the function that you want it to carry out, okay, is coded through software. Let me explain in passing. Think about two devices. One is a small footprint device. The other one is maybe a server. Okay, it's a big server. Now, the resources that the server requires in terms of network, right, and also computing power and storage as well as computing power inside the cellular network are much higher compared to, say, a small footprint device. Okay, so depending on what the small footprint want to do and the server want to do, they'll be given a slice of the network, right, that's able to handle the job that they want to do. Okay, and that's where the idea of a software-defined network comes in, right? So we'll mention that in passing, not in a lot of detail, okay? As well as what's called network function virtualization, right? Virtualizing network functions, right? And that's where that's the strength of 5G systems. Okay, I think I've said what I needed to say with respect to what you're going to do in these what you're going to do in these in this course. So I don't know whether there is any question. I don't know whether there is any question so far. Yeah. Now I am proposing that we will stop. We will not go all the way to 9 for today's class. I'm thinking that maybe I talk a bit about this first introductory topic. All right, maybe just touch a bit on it, and then we'll really get into details starting on Tuesday next week. Does that sound like a plan?
Yes.
Is it a good plan? It can be a plan, but a horrible one,
It's a very good plan, bro.
Okay, thank you, Richard. So it's a reasonable plan,
Yes.
Okay. So I think what we'll do, let me just. Oh, if there is no question. Oh, okay. Maybe I should have gone a bit down on this. Maybe just to highlight. I showed you the course texts. So these two books, those are the course of what we need. Yeah. I think delivery. I think it will be physical, other than this first maybe 2. I don't know. Maybe 3 weeks. We don't know. We don't know. We'll do a few labs, like we said. Those are the two key books. The others you can find in the library, right, to supplement what we're talking about. We'll have a number of quizzes, a number of assignments, and the 2 exams. All right, but the key thing is the 50% is exams, and the other 50% is continuous assessments. All right, continuous assessment. Now, I think here we're going to have some marks for labs. What you're calling assignments here, there will be some for labs. Okay, we'll see how to do that splitting as we go along. And I think that's really it. And that's a grading system. That is a grading system. So please get a copy of this and start looking at all these different ideas. Okay, so if you are fine, let me now stop sharing the outline and talk a bit about the introductory topic. So let's see, note that. We want let me get it. By the way, what do you think about what we've just talked about? Does it sound hard? Does what is lying ahead of us? Does it sound hard or doable?
Only time will tell, Prof. I mean, as long as there's no MIPS, I think we should be okay.
I think
as long as you don't have MIPS.
Sorry. It doesn't sound hard, but I remember you saying that there'll be a bit of calculation. Can you confirm if calculation is still there?
Yes, we have calculations, yes. I think I mentioned. Oh, sorry. I think, Muruki, just a second.
Okay.
What am I saying? When you're talking about let me see, understanding signals, we'll do a few calculations there about understanding signals. When you're talking about understanding wireless networks, we'll do some calculations, a bit of calculations there. Those antenna things, there'll be some calculations. And then also, when talking about coding and error control, there'll also be some logic, because it's really is application of logic. All right, that you'll have to do. So a bit of calculation, but mainly logical reasoning based on what the model, right? How the model ought to be executed.
Okay.
Yeah, that's what it is. Muruki, please go ahead. I don't know whether you are talking. Oh, was it Muruki was talking? I'm not sure. Can you see the hand is up? Please go ahead. Moreithi, Morioki, can you hear me? Okay, maybe something happened there. All right, so let's continue. So we were sharing these. Where is it? All right. Yeah, we're sharing this first topic. All right. So I think these first 1-2 slides basically is just basic information. Yeah, I think most of you know where my office is. I think I've only seen one new student. Is that Shira? I think it's Shira. Is the only new student I've seen. The others, yeah. So my office is on the 3rd floor, Shira, room number 7. Those faculty offices up there. Yeah, and of course our class will be between 6 and 9. Physical, other than these first few classes. So let's now talk a bit about this intro to networks and wireless communications. I think I've already talked about the topics we're going to cover. Right? Part 1 is the technical issues about TCP/IP and so on. Part 2 is wireless technologies. Part 3 is again wireless, but focusing on the 802.11 and Bluetooth. 802.15 is Bluetooth, and this is Wi-Fi. Okay, Wi-Fi. There are a few others, like ZigBee. This one is used in factories. Part 4, wireless networks, focusing on cellular technologies, and I think I've quite expounded on these 4. So those are the 4 areas that we'll be focusing on across the entire semester. Right, entire semester. Yeah. So this introductory topic, we want to talk about these couple of things. Right. Starting with a bit of an intro, saying why wireless is important, the impact it has on us, and then talking about the global cellular networks. All right. Mobile devices, we know they have come and they have really changed things. Okay, what's likely to happen in the future? There are some issues with the wireless, and we need to solve them. How do we deal with that? All right, how do we do it? And basically, this is to do with errors. All right, with errors, and therefore the coding that I talked about earlier. That's where we need to focus on, and then the rest of the topics. Okay, so I think we know that communications really started. That is wireless started with Marconi, the inventor of the radio. Okay, way back in 1896. And he was able to actually encode alphanumeric characters in an analog signal. Okay, so analog signal able to place letters of the alphabet and numerics, right? And they are transported and being able to be decoded. Let me use that word, decoded on the receiving end. Okay, yeah, and these of course they were able to send telegraphic messages from Europe to the US. Satellites came in 1960s. Okay, and again these revolutionized communications. Okay, in 1960s. Then over time, okay, wireless communication has evolved over time. Okay, starting with radio, then TV, mobile telephony, mobile data later on, and of course satellites. We use satellites quite a lot. Quite a lot nowadays. Although for earth communications, we don't rely too much on this. Okay, satellites for communication, we use them for other things. Like for example, weather prediction, and so on. As well as, of course, for example, the military use them a lot. Okay, use them a lot for command and control. Yeah, but what I was about to say is for communications nowadays, we tend to use fiber cables, right? Submarine cables to interconnect continent. Okay, that's the one we use mostly, right? Yeah, and of course, with cellular technologies, things have changed quite a bit. Okay, we know IoT. And the way you think about IoT basically are small devices, okay, like microcontrollers. They are sitting somewhere, in a remote place. Maybe it's a farm. They are collecting data. Maybe they are sitting on a wild animal, all right, and you're tracking what's happening to that wild animal over time. Okay, so they are small things, but they are connected together. Okay, so it's actually an Internet of Things, right? Internet of Things. But for that to happen, we need communications, right, to work properly. Okay, to work properly. Now, cellular telephones, of course, initially we had the fixed telephony, wired telephones, all right? So this became like a replacement in some cases, okay? The first generation was only offering voice, okay? And the second generation had a bit of limited data, So the first one, which was purely analog, that is all this is a cellular, 1G was basically voice, okay? 2G was able to do voice and a bit of data, not very high speed, okay? Not high speed. But third generation, fourth generation, as well as fifth generation, these ones are able to carry multiple, right? Multiple services. There are some examples here of the different kinds of services. Today, for example, you use your phone, for example, to talk to your friends face to face, okay, going through the cellular network. Of course, if you're using let me see, if you're using a WhatsApp, it's not necessarily true that you're going through the cellular network. You can get going through the internet directly. Okay, that is the internet paths. But I think you get the point. Anyway, so 3G all the way to 5G, all right, we have a variety of services. A variety of those services. The impact has been quite profound. Okay, that is, ability to communicate wirelessly has really changed the way things work. So you might think of say social networks, right? Social networks, okay, or even the way, for example, people form groups, even to solve problems. All right, maybe somebody is sick, was hospitalized for quite a while. The bill is heavy. They form groups. They collect money through these social, for example, WhatsApp groups. Okay, you can see the impact that they have had. In the past, for example, raising money was very difficult. All right, it was very difficult because getting, all your friends and the friends of your friends and friends of those friends, right, to come and join was not always that easy. Okay, but anyway, the impact has actually been there, right? So this tends to kind of shrink the world. Okay, you talk of a world being a small village. It's always generally think of it as an always on network. Okay, for example, SMS is an always on. All right, even when your phone battery dies, your messages, the ones you have already sent or that have been sent to you, you'll still receive them, okay, because they're always on network. All right, it's always connected. Okay, it's always connected, and there is convergence. Right, there is convergence of services as well as technologies. All right, as well as technologies. This one is an attempt to show, if you like, what has happened with communications over wireless specifically over time, okay, from 1930s to about 2020. All right, 2020 was really the birth of 5G. Okay, so you can see radio, the original radio really came just before the start of the Second World War. Okay, the Second World War. And then TV, black and white TV, was introduced around 1950. All right. Please note the y-axis. This one is the frequency part of the spectrum. Okay, where each of the technologies lies, and this, of course, is a time. So, for example, you can see black and white TV required 30 megahertz. Okay, bandwidth. Two-way mobile radios, okay, in the 1960 mid 60s, roughly about 300. Not this log scale. The the part of the spectrum here is log scale, right? Again, requiring about maybe 100 megahertz or so. FM radio, 100 megahertz, okay, introduced before 1960s, all right? Color TV introduced 1970, all right, requiring 300 megahertz, okay, carrier, carrier signals. And then if you check up here, experimental satellite communications, they started, satellites were introduced in the 60s, but the experimental ones were about mid 60s, right? To check what was possible, what could be achieved, right? And you can see, for example, the ability to send man to the moon in 1969 depended on these satellites, okay, to be able to, for signals to be able to be communicated between Earth, the moon, right, and the vehicle as it was moving towards the moon. All right, terrestrial microwave operating at about almost between 3 gigahertz and 30 gigahertz, okay, which is generally the range for satellites. Okay, that's where you find the terrestrial microwave. Okay, introduced early 1970s. All right, and then communication satellites introduced 1980s. All right, 1980s. And then you can see, for example, cellular phone in the early 1990s. That is the 1G. All right, Wi-Fi introduced in the early 90s, around 1992 or 1992 there also. And then 3G in around 2000. 4G actually from around 2010s. Okay, and then 5G 2020 and IoT. Right, and then you can see also up here optical communications and infrared wireless. All right, infrared wireless. This is the one you use, for example, for your remote control. To control your TV. Right, to choose channels and so on. But of course, it can also be used for actual communications. Right, so you need infrared is just below the visible part of the spectrum. Right, just below that. Optical, of course, is in the range of the visible light. Okay, visible light. There's a small one here I want you to just note, millimeter wave. This one here. This one is actually designed to work together with 5G networks to make it even better. To make 5G networks work even better. But here is for Wi-Fi. Okay, but for high-speed communications, millimeter wave is actually expected when you're moving towards 6G. All right, to play a big role. And so you can see what has happened over time. Right, what has happened over time in terms of these different technologies. So for cellular, again, this is just like a comment on what you're seeing on that graph. In terms of users, starting with about 11 million in 1990, growing to 8 billion in 2022. All right, you can see it's a massive growth. All right, in other words, users of cellular telephony. Okay, of course, mobile devices are quite convenient. Okay, they are location aware. That's why you're able to use them, for example, for navigation. Okay, yeah, and they're actually quite economical, so that individuals can use them, and you can use them in all kinds of places, all right, including very remote parts of, for example, our country, as long as there's 2G. Okay, as long as a provider has put a tower there, and they're able to communicate. Yeah, so these are the 5 generations of the cellular technologies. Okay, starting with 1G, which was analog, pure voice. 2G was analog voice and digital. Sorry, let me rephrase that. Was analog in terms of switching, okay, in terms of switching, but it was able to. It could carry a bit of data. It could carry a bit of data, right, at moderate rate. What this means, moderate rates. This one is roughly about 14 kilobits, and this is true. Hold on a second. Yeah, 14 kilobits for the original one. But when you get to about 2.5G, that is edge, you can move this to about 170, right? 171 kilobits per second. Okay. 3G, the technology changed. So maybe just a quick one. We'll talk more about this. 2G was using FDMA and TDMA, time division multiple. That is terms of multiplexing, time division multiple access, and frequency division multiple access. I'll talk more about this, all right? But basically, in passing, what it means is you create a frame. The frame is in a portion of a spectrum which is 200 kilohertz. That 200 kilohertz is split into 8 time slots. All right, and then those 8 time slots are then allocated to wireless devices. Sorry, for example, phones. All right, so one phone can be allocated 1 slot. If it's moving data, it can have more than 1 slot, maybe 3. Okay, and then the others. So, and that would be called a burst. So you send a burst of 200 kilohertz having 8 time slots, and that is 1 frame. All right, and that is a 2G networks, right? 2G networks. Anyway, so just mentioning that in passing. And then what would happen is, because you want to be able to have multiple users on this, you take 50 megahertz. That is the spectrum for 2G, even 3G. That's true. You take that spectrum, okay, and then you split it into 2. 25 kilohertz for downlink, 25 kilohertz for uplink. And then the 25 kilohertz is split into 200 kilohertz each. So 200 kilohertz will be 1 channel. And then that channel, you split it time slots, right, to create a burst of signals. Anyway, so that's how that 2G works. 3G, I think I already mentioned the idea of CDMA. Okay, it falls under this general category of UMTS, Universal Mobile Telecom Systems. The reason why this became important is, if you go, for example, the US system, all the way from 1G, was actually using a CDMA, right? Whereas the rest of the world, Europe and the rest of the world, was using FDMA, TDMA, right? Whereas the US was using code division. In other words, the idea of spread spectrum, all right, is a key difference. It's a key difference. Anyway, so when people now wanted to create 3G, the ideas converged, and they decided to go to spread spectrum, because it works better than TDMA and CDMA, okay? And CDMA, right? So that is the idea. And of course, all based on packets. It's digital and based on packets. But it was still compatible. 3G is still compatible with 2G, So in fact, you have two networks. There's a network that is analog. That is that is 2G, and then the 3G, all right, which is able to handle packets, and I'll explain how that works, all right, is another network, but they work together in one cellular provider. And then 4G using an OFDM. I've already talked a bit about these ideas, and by the time you get to LTE, you can go to 100 megabits per second there. Right, 100 megabits per second. But with 5G, you can go to 1 gigabit per second there. Right. It's also true for 4G. Right. This can be pushed to 1 gigabit per second. Right, for low mobility users. In other words, where you don't need high speed there, where you don't need the high speed. Right. And then 5G. These are just some use cases. Right. 3 of them according to ITU. Right. According to ITU. So those are the 5 generations, and what they really were designed to focus on. Okay. Mobile devices, of course, has changed over time. Okay, that is a revolution of mobile, devices, starting with by the way, let me ask, when you talk about a Mulikamuizi phone, which generation do you think that one is? A Mulikamuizi phone, where do you think it falls in with these generations?
Does it fall between 2G and 3G?
Between 2G
and 3G.
And 3G, and actually that's true. It's 2.5. It's actually 2. So a Mulikamuizi is a 2.5G phone. All right. By the time you come to 3G, that's a smartphone. All right. That is a smartphone. Anyway, so you may not know this. Like, for example, in the early days, one of the popular phones was called Nokia 310. All right, so a very good 2G, 2.5G phone. That was like the top of the range. Those are the days, right? And if you even go back a bit further, like for example, in this country, the beginnings of cellular communications, even before Safaricom was formed in 1999. But before it was formed, Telecom Kenya had already started introducing that idea of cellular before the company was formed, right, as a Safaricom, right? And the phones then were, I think you've seen handheld sets, but I think they're called cordless. You've seen cordless phones used inside the house. You can imagine that size, about half a foot, right? Yeah, 10, 15 centimeters, in terms of, so big with a massive antenna, right? An antenna probably like, a whole 5 centimeters protruding out. So, and that device, of course, it will be owned by people with money, right? Each of those would cost like 200,000 Kenya shillings, in those early days. Just taking you a bit back, giving you a bit of a throwback, right? So that was in the late 90s, right? Late 90s. What the experience in this country of cellular technologies, right? And then, of course, once 2G now became deployed, right? Then you're able to have it made a business sense, right? And companies like well, there are many, like Nokia, like Siemens, Motorola, and others, right? They decided now to focus on developing those small devices, right? Anyway, so so you can see there's been a change, okay, from those very early phones to your 5G phone today, okay? Your 5G phone today costing you, upwards of 100K, I don't know, 150K and so on, 200,000 shillings, depending on the model, okay? Yeah. So please note these have several onboard sensors because they have accelerometers for doing different things. Right. They have many megapixels so that they can take images and so on. Right. And of course they can handle high speed. And most importantly, from 4G to 5G, they're able to do actually all the way even the 2.5 G and 3G. They must be able to do signal processing. Right? In other words, the computer inside the phone, right, that processor is busy executing algorithms, and the job of those algorithms is to process signals, right, for sending out and for receiving. I'll explain this a bit more as we go along. Okay, as we go along. Yeah. Anyway, yeah, I think I want to stop. I want to stop here. I don't think I want to be able to finish this for today. So is that okay, good people? I wanted to introduce this just a bit, and then yeah, I'll talk more about this in the next class. Is that fine?
Yes,
Yes.
Prof.
Yes.
Okay, all right. So maybe we can take attendance. By the way, is there any question? Is there any question on the introduction, overall introduction of what we have set ourselves to do? If not, I think let's take attendance. So I need to share this. So let me do that. Evans, you're still recording, eh? Hello, Evans.
Yes, I am.
Okay, that's great. For those who may have missed, they can go through these. So where will you store? Will you store this?
I'll
Evans?
hand it over to you tomorrow.
No problem. Or physical, eh?
Yes.
Physical handover, eh?
Yes.
It's I think it's usually big. Yeah, I think the upwards of 100 MB. That's or even if it's not tomorrow, just keep it somewhere.
Yeah.
Yeah, then I'll organize so that it can deploy it on
All
Blackboard.
right.
Yeah, that's okay. Let me stop sharing this, and then we share the class list. today's attendance. Okay. I hope you can see your names, eh?
Yes.
Yes, we can.
Okay, great. So if I skip yours, you let me know if I make a mistake. Abel, you're with us?
Yes, sir.
Okay, that's great. Arnold?
Yes, sir.
All right. Osawalu? Osawalu, are you with us?
Yes, I am. Yes, I am.
Okay. It was going to change to an N. Eh? All right. Joyce?
Yes, I'm here.
Okay, that's great. Levy?
Yes, I'm here.
That's good. Sheila?
Yes.
All right. Welcome to our class, Sheila. I think you are the only, if I've seen this correctly, I think you are the only new one. Eh? All right. Welcome to our class. Eh? Have we shared the class before? I don't think so.
We have last year. I did the first semester last year.
Oh, okay. All right.
Yeah.
All right. Okay, great. I think I'll once we meet in campus, it will come back. Leigh Frank, are you with us?
I'm here.
All right. David. Hi, David. David, are you with us? Kenneth?
Yeah.
Who? Is that David or Kenneth? Who? Kenneth. Eh? So David is not here. Eh? All right. Ken, you're still here?
Yeah, I'm here.
Okay. Patrick, you're still with us? Hello, Patrick. Steve?
I'm here.
That is Steve, eh?
Yeah.
Okay, great. Wellington? Wellington? Not with us. Caroline?
Present.
Caroline is with us. Gloria?
Present.
Okay. Emmanuel?
Present.
Emmanuel? Okay, Emmanuel is with us. Morioki? Morioki is still with us. I'd seen him. His hand was up. I don't know what happened. Morioki?
Just texted you. He's there.
Oh, he's there. Okay, fine. Oh, okay. He's probably having an issue with this. All right. Salah?
Present.
All right. Wilberforce?
Present.
All right. Moses?
Yeah.
Okay. Evans is recording for us. Richard?
Here.
All right. Fred?
Present, Prof.
Okay, great. Hi, Nick. You're with us? Hello, Nick. Nick is not with us, eh? Oops. Do that. Second. Where is Nick again? There we go. Yeah, Said.
Sorry, Prof. Prof,
Who is
sorry.
that?
No, it's
Who is
Richard
that?
speaking. It's Richard
That's
speaking.
Nick. Oh, Nick, eh? That's
Hello?
Nick, you're with us? Hello, Nick. I'm not sure. I'm just looking at the attendance list. I'm not seeing. I'm not looking at your microphones. I don't know who is talking.
Prof, hello?
Hi. Hello?
Yeah, this is Richard speaking.
Hi, Richard.
Yeah, I'm saying I think you messed up my email when you tried to like update Nick's.
Did I? I copied.
Yeah.
Yeah. Yeah. Okay, I got it.
Maybe just undo. I think that should like fix the.
Yeah. I need to undo a few. Okay, let me just undo 1, 2. Yeah, that's here now. So I just need now to go back to Nick. Okay, so Said is here. Yeah. Yeah, he's around. Leonard, you with us?
Yes.
All right. Kevin? Kevin is
Present.
still with us. Christopher? Christopher, hi.
Present.
Okay. Enid?
Present.
All right. And Timothy?
Present.
Okay, fine. I think most of us are here. Just maybe 2 or 3, yeah? Okay, good people. Hello?
Yeah, Patrick is also here. He has issues with the speaker.
Who?
But he's Patrick.
Who? Patrick, eh?
Patrick, yes.
Oh, let me locate Patrick.
Number 11.
Oh, okay. Here, eh? Oh, he's there, eh?
Yes,
okay,
yes.
Fine. Okay. Is there anybody I've said is not there? Like, has Nick written? Nick? Okay. Anyway. Okay. So I think good people. Let us stop here. So I think Evans, you can stop recording now, eh? And we'll meet next week virtually, I guess.